cosine, or cosecant and cotangent, is you want to make a u substitution. And you want to pick u so that, well, for sines and cosines and secants and tangents, there's a very kind of interesting way I like to think about it. I'm going to make the choice for u so that whatever isn't u, after I deal with the du dx interchange, there is an even power of the non-u choice left over. So watch me make the wrong choice right now. This is the wrong choice. In fact, let's do it in a different color. I'm going to make the choice of u equal to secant of x. And the reason this is the wrong choice is because my du is the derivative of secant, which is secant x tangent x dx. So if I take out a secant x and I take out a tangent x, I'm left with a secant and a tangent. And the problem is I can't really do anything with that. If I have a secant x tangent x tangent x dx, there's my du. U is secant, so there's my u. But I don't know what to do with tangent. That's not entirely true. We could do something with tangent, but it's gross. There's an easier choice to make. The easier choice here is to actually let u equal to tangent of x. Not all this. Because if u is equal to tangent, I'm going to save this one for a second here. Then our du, the derivative tangent is secant squared x dx, which is right here. And so when I start making the change from x to u, I get the integral of, well, secant squared x dx is my du. And then I'm left with a tangent squared. And I want the oh, sorry, that one's, I made this one too easy. Yeah. Sometimes I make the problems too easy accidentally. That's going to be super easy. That's going to be u squared. Okay, that one was too easy. It's fine. So we're going to get u cubed over 3 plus c, which is going to be u, which is tangent x. We still want to make the choice, so we still follow the rule, even though it was kind of lame. Right, we picked u to be something, and then after we dealt with du, there was an even amount of the non-u choice. The non-u choice here being secant, and there was 0 of them left over, which is still an even number. Let's look at this problem, which is a little more interesting. Let's write it on the other side. Oh, I already had a problem. We'll come back to that. So let's look at the integral of secant cubed x tangent cubed x. I'm either going to pick u equal to secant of x or u equal to tangent of x. And here I'm going to pick u equal to secant of x. Why not tangent? Well, because I pick u equal to tangent, the derivative is secant squared. That takes away 2 of these secants and leaves an odd number of, oh, that's fine. Sorry. Gosh, I keep like, yeah, my brain, no, sorry. I'm sorry, yeah, if u is tangent, then du is secant squared. You have an odd number left over after you deal with du, and that's a problem. Instead, I'm going to pick u equal to secant, because then my du is secant x tangent x dx. I don't care which way you get there. I personally prefer to write this out so that you can see this part all by itself. So I'm going to rewrite this as the integral of secant squared x times tangent squared x times secant x times tangent x dx. Still the same thing, right? Secant squared times secant is secant cubed. Tangent squared times tangent is tangent cubed. There's du. U is equal to secant, so there's u squared. And the non-u thing, tangent squared, or I should say tangent, is raised to an even power. And the reason we want that is because then we can use a trig identity, right? My favorite trig identity. I tan and get sexy. Right? You guys have heard me say that one before. If you haven't, now you have. Add tan and get sexy. Can never forget it. Anyway, 1 plus tangent squared equals secant squared. So tangent squared x equals secant squared x minus 1. But secant was our choice for u. So tangent squared x is really equal to u squared minus 1. So we plug that in for tangent squared. And then this becomes the integral of u squared times u squared minus 1 du. We multiply it out. That's going to be the integral of u to the 4th minus u squared du. That's going to be u to the 5th over 5 minus u cubed over 3 plus c, and then replacing u with what we said it was in the beginning, secant. That's going to be secant to the 5th x over 5 minus secant cubed x over 3 plus c. Not too terrible. So there is kind of a way of writing the rules. I never remember what they are. If you look back at the handout, so if you look back at the handout, let me share my screen for 1 second. Share the right screen. If you look at the handout, it says if secant is an even power, then, or secant is 2 an even power, you're essentially going to let u equal tangent. If tangent's to an odd power, you're going to let u equal secant. I can never remember that. I feel like that's impossible to remember. So instead, I just kind of try and think through. Meaning, let's do a different example. Let's do secant to the 4th, tangent to the 4th. Secant to the 4th x times tangent to the 4th x dx. Again, I can't remember which one is which. So I'm just going to think about, well, if I let u equal secant, my du is going to be a secant tangent, which means I'm going to be left with a secant cubed and a tangent cubed. Secant cubed will be fine, because that's u cubed, but tangent cubed is a problem, because tangent cubed, there's not a nice trig identity for that. On the other hand, if I let u equal tangent of x, then my du is secant squared x dx. And then when I take that out from my secant to the 4th, there's still going to be an even amount or an even power of secant left over. So you're always trying to leave yourself with even powers of your trig functions that are not your choice for u, because those are going to lend themselves to nice trig identities. In case we've forgotten, and the trig identities that we're using here really are, well, for the sine and cosine, right? It's cosine squared x plus sine squared x equals 1. And for the secant and tangent ones, it's 1 plus tangent squared x equals secant squared x. There's also one for cotangent. It's 1 plus cotangent squared x equals cosecant squared x. So here, let's see. So du is secant squared. So I'm gonna rewrite this as the integral of secant squared x times tangent to the 4th x times secant squared x dx. And then it's just replacing things with u's. There's my du. So I better tangent to the 4th, that's going to be u to the 4th. And secant squared, well, secant squared is equal to 1 plus tangent squared. Tangent is u. So secant squared x equals 1 plus tangent squared x, which is u squared. So that's going to be 1 plus u squared. And then you're going to get the integral of 1 plus u squared times u to the 4th. You always will have to multiply this out before you can integrate. So you're going to get the integral of u to the 4th plus u to the 6th du, which then becomes u to the 5th over 5 plus u to the 7th over 7 plus c. And then you plug back in what u is, which is secant, which is tangent, and you get tangent to the 5th x over 5 plus tangent to the 7th x over 7 plus c. So that's kind of how these secant tangent ones work. I will say 2 things. So I've done ones where the powers are both odd or even because they kind of can only be done one way. But if you happen to have one where, well, so there's two other options. You can have one even and one odd, and one of them is nice and one of them is awful. So let's say I wanted to do the integral of, say, secant to the fourth x tangent cubed x. Now let's make it secant to the sixth. We have a ton of fun. In this case, you could make either choice. You could make the choice to let u equal, let me just throw this kind of trash. You could make the choice to let u equal secant x, and then du would be secant x tangent x dx. And the non-u choice, tangent, is the not u choice. Well, after I deal with this, there's going to be an even number of tangents left over, so we're good to go. So we would write this as the integral of secant to the sixth x tangent squared x times tangent x. Oops, no, I wouldn't. I would also pull out the secant x from here. I'd write this as secant to the fifth x times tangent squared x times secant x tangent x dx. And then there is your du. Secant to the fifth is u to the fifth. And tangent squared, let's see, 1 plus tangent squared x equals secant squared x. So tangent squared x equals secant squared x minus 1. So tangent squared x equals u squared minus 1. So that's going to be u squared minus 1. And the rest is pretty straightforward, right? You're going to get the integral of u to the seventh minus u to the fifth, right? Multiplying this out. And then integrating, you get u to the eighth over 8 minus u to the sixth over 6 plus c. And finally, you plug back in tangent, secant. And you get secant to the eighth x over 8 minus secant to the sixth x over 6 plus c. I do want to mention you could have made the other choice here. You could have said, oh, I don't want to pick secant, I want to pick tangent. So if u is tangent x, then du is going to be secant squared x dx. And I can rewrite this as the integral of secant to the fourth x tangent cubed x secant squared x dx. This is worse. It'll still work, but it's more work. Secant squared x dx is still du, or is du, I should say. Tangent cubed is u cubed. But secant to the fourth is more effort. Secant squared is 1 plus tangent squared. So in this part, secant squared is 1 plus tangent, which is u squared. So then secant to the fourth is secant squared squared, which is going to be 1 plus u squared squared. So typically, if we have the choice, it is usually correct to make the choice where you're letting u be the function that is raised to the higher power, because you're going to end up doing less work with the trig identity for the other parts. Right? So here you're letting u equal secant, which was raised to the sixth, ended up so we didn't have to do any of this like squaring this out. But we could do it this way. We could do 1 plus u squared times u cubed and then integrate all of it. Right? But it wouldn't be impossible. It would just be annoying. But I don't want to finish this one because. So I will mention though that if you do finish this one, you get an answer that looks like I said I wasn't going to finish it. Now I'm going to finish it. So let me just erase here. So if you do it this way, you end up getting an answer that looks different. 1 plus u squared squared is 1 plus 2u squared plus u to the fourth times u cubed du, which is going to be the integral of u cubed plus 2u to the fifth plus u to the seventh du. Which is then going to be u to the fourth over 4 plus 2u to the 6th over 6 plus u to the 8th over 8 plus c. And then you plug back in tangent, and your answer is tangent to the 4th x over 4 plus tangent to the 6th x over 3 plus tangent to the 8th x over 8 plus c. Are these the same? Actually, yeah. Well, at least up to a constant. So I know they don't look the same, but if you use trig identities where you use the fact that secant squared equals 1 plus tangent squared, you could, through a lot of work, change this into that or vice versa. You might be off by a constant, but essentially they're the same. That said, I would definitely do it this way. That is the easier way. Okay, so the last thing I'll say about these secants and tangents is there's only one type of integral or one combination of powers of secants and tangents that you cannot do this for. And that's when you have secant to an odd power and tangent to an even power. So if you have like the integral of secant cubed x dx, or even grosser, the integral of like secant cubed x times tangent squared x dx. That is a harder question to answer. We cannot do a u substitution for this problem. Maybe at the end of the day we'll talk about this because it actually is a problem that requires integration by parts. And I feel like we should use some more integration by parts before we go to that. Okay, and then I should ask, yeah, I might regret asking, does anyone want to see how to integrate sine to the 4th? It's okay if the answer is no. It's also okay if the answer is yes. Okay, yeah, we should. I was kind of hoping you guys would say no because it's just kind of gross, but we should do this problem. Okay, so I've seen some people do crazy things where they do integration by parts for a problem like this. You should not do integration by parts for a problem like this. I mean, you can, but I will fully admit I don't actually know how to do it using integration by parts. Although it is definitely possible. Or at least it's possible for sine squared. I think it's possible for sine to the 4th. That is also something we should point out. There are some integrals that can be done using a variety of methods. Some things, not a lot, but some of them do lend themselves to more than one method of integration. But I'm going to write this as sine squared x times sine squared x. And then I'm going to use the angle identities for sine squared. And I should point out, right, there's two different identities we're talking about for sine squared. I'm not using the one that we just were using, the sine squared x equals 1 minus cosine squared x. That is not the identity I'm about to use. I'm going to use the identity that sine squared x equals 1 minus cosine of 2x divided by 2. That is the identity we're going to use for sine squared. So this is going to equal the integral of that times itself. Gross. So what I would do is I would bring out the 1/2s. So 1/2 is a 1/2 is a 1/4. And then I'm going to multiply this out. So 1 minus cosine of 2x times 1 minus cosine of 2x is going to be 1. And then it's going to be a minus cosine of 2x minus another cosine of 2x, so minus 2 cosine of 2x. And then plus cosine squared of 2x. Come on, button. Okay, there we go. And now we have to use the identity again, right? Except instead of for sine squared, it's for cosine squared. So we're going to use the identity, and I'm going to be extra careful about this. Let me see, I'll give us a little more room. I'm not careful about pens though. So we know that cosine squared of x is 1 plus cosine of 2x over 2. So cosine squared of 2x is going to be 1 plus cosine of 2 times 2x. Or 1 plus cosine of 4x all over 2. So we end up getting, this is where things start to get really messy. We get 1/4 times the integral of 1 minus 2 cosine of 2x plus cosine squared of 2x is 1 plus cosine of 4x all over 2. Okay, I would much rather write this the following way. I'm going to write this as 1/2 plus 1/2 cosine of 4x. And while we could put those together, we don't really need to. So let's integrate this. I guess I should not erase this because we might want to look at it before we finish it. So let me write it on the other side. I guess I might as well combine things that combine since we're going to the other side of the board. So that 1 plus the 1/2 will become a 3/2. So I've got a 1 plus a 1/2, which is 3/2. I have a minus 2 cosine of 2x. And I have a plus 1/2 cosine of 4x. And if you're reading solutions for a problem like this, you will often see people factor out a 1/2. And so you'll often see people rewrite this as 1/8 integral of 3 minus 4 cosine of 2x plus cosine of 4x. Just so they don't have to deal with the 1/2. I don't think we really need to do that, but it is often something people do. So let's integrate. We get 1/4. Integral of 3/2 is 3/2 x. Integral of cosine of 2x is going to be sine of 2x over 2. Integral of cosine of 4x is going to be sine of 4x over 4. And then we would simplify it. I would probably distribute the 1/4. So 1/4 times 3/2 is 3/8 x. 1/4 times negative sine of 2x is negative 1/4 sine of 2x. And 1/4 times 1/2 times 1/4 is 1/32 sine of 4x. Kind of gross. Don't even ask me about this one. Because then you'd have to do 3 of those things multiplied together. This is kind of insane. And it's not that insane, but like it's kind of insane. Are there questions about anything we did here? We can go back to the other side if you want. We wrote sine to the 4th as sine squared times sine squared. We replaced sine squared with 1 minus cosine of 2x over 2. There and there. We multiplied it out. We brought out the 1/4. We rewrote the cosine squared of 2x as 1 plus cosine of 4x over 2, which is just this part right here. And then we put some things together, integrated everything, we got an answer. Okay. Yeah. So let's do some more integration by parts. Let me take a look so I don't miss anything that's really vital when it comes to integration by parts, because there's definitely a lot of things. Oh, we didn't do any of those. Let's do some of those. So I don't believe we did anything like this. Let's like x to the 6 times natural log of x. First of all, is this an integration by parts problem? Can I do it? So when I'm thinking about how I'm going to integrate a thing, I usually first ask myself, well, first I see it is a mixture, right? I've got an algebraic thing times a logarithmic thing. The second thing I ask myself is, can I do a u sub? Because at least for me, I feel like a u sub is easier. So I'm never letting u equal x if it's a u substitution. But I will ask myself, can I let u equal natural log? I could, but then the derivative is 1 over x, and I don't have a 1 over x. So it's probably not a u substitution. It's probably integration by parts. So if it's integration by parts, what am I going to choose for u in this instance? Am I going to choose the x to the 6th, or am I going to choose the natural log of x? Yes, right? Because Mariah knows, and then many of the rest of you know as well, the acronym LIATE. Or if you're taking the 16 series, the acronym LATE, because they don't talk about inverse trig functions in the 16 series. But yeah, LIATE. For first we pick a logarithmic function to be our u. Oh, we've got a logarithmic function. It's our u. And then I always just write down dv and x. Even though I want to take the derivative here, I really want to make sure I get dv right. dv is everything else in the integral. dv is x to the 6th dx. And then I write down the rest of the stuff. du is 1 over x dx. v is the antiderivative of x to the 6th, which is x to the 7th over 7. So then I'm going to rewrite this, and I always feel like I put this in the wrong spot. So this is going to be equal to u times v, natural log of x times x to the 7th over 7, minus the integral of v du, x to the 7th over 7 times 1 over x dx. And here's where we have to remember the whole point of integration by parts. The whole point is that you rewrite the integral so that this new thing you're integrating over here is easier to integrate. And while it might not look like it at first, it is, because we can simplify this. An x to the 7th divided by an x cancels out one of those x's. So whenever you got something like this, you need to combine it together, simplify it, so that you've really got natural log of x times x to the 7th over 7 minus 1/7 times the integral of x to the 6th. I've seen too many people get to here and then say the antiderivative is x to the 8th over 56 times the natural log of x. We can't just integrate the factors and multiply the answer together. If we could, we would have done that over here. So we're going to get the natural log of x times x to the 7th over 7 minus 1/7 times x to the 7th over 7 plus c. Which you could leave like this. Maybe you would simplify it a little bit. I don't think we can simplify it. What about, sure. What about something like this? The integral of x times sine of 5x squared. It's definitely a mixture. I've got algebraic and trigonometric things. Integration by parts? Well, no, wait. First I should ask, is there a u sub? Can I let something equal u that's going to work out nicely? It can. Here I can let u equal 5x squared, and my du is going to be 10x dx. I have an x dx, so 1/10 du is going to equal x dx. So here I would have, this is going to equal the integral of x dx is my 1/10 du. And then 5x squared is just u. So this is going to be sine of u. This is going to end up being 1/10 times the integral of sine, which is negative cosine of u, plus c, which is going to be negative 1/10 cosine of 5x squared. Definitely not an integration by parts problem. Another way to see it's not integration by parts is that if you were going to try doing integration by parts, you would be wanting to let u equal x, and then your dv would be sine of 5x squared, and sine of 5x squared can't be integrated, not on its own. What about this next one? What about, where'd you go? On the other hand, yeah, so let's just change this problem seemingly slightly from x times sine of 5x squared to x squared times sine of 5x. Now it does require integration by parts, because the only real logical choice for a u substitution here would be maybe 5x. If u is 5x, the derivative is 5. And while that's fine, it doesn't help me deal with this x squared here. So this is, so, and really kind of the real difference between a u sub problem and an integration by parts problem is, in a u sub problem, you have essentially like a reverse chain rule thing going on, right? You have a function of a function and the derivative of that function showing up. Whereas in an integration by parts problem, you more have a product of functions that don't really interact well with each other. One of them, there isn't a derivative of one of them showing up in the other one or something. Now, we could do this one the long way, or we could use tabular. I'm going to use tabular. And then if you guys want, I will definitely do it the long way. So again, I'll remind you, the tabular method only works when you have x to a positive integer power times a sine, a cosine, or an e to the something. Those are the only three things where it works. And really, the way I can remember it is the derivative of x, the derivative of your u thing eventually has to become 0. So here's our tabular method. What would we choose for u? X squared or sine of 5x? You guys, like, he already knows the answer, just let him say it. Nobody. Fine. Our u is x squared. Okay, someone said something. Great, thank you. And then we take the derivatives. Derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. And you do want to go all the way to 0 because you need that many rows in your dv column. Just like with regular integration by parts, dv is everything else. So if u is x squared, dv is sine of 5x dx. It's too bad I never came up with this method, didn't pick letters that looked less similar, because oftentimes I'm writing u's and v's and they start looking a lot the same. So be careful with your u's and v's, they can start to look the same. So dv is sine of 5x. And then we're going to anti-differentiate. So I know the derivative of sine is positive cosine. I know the antiderivative of sine is negative cosine. So it would be negative cosine of 5x divided by 5. I'm trying to keep my rows there. Okay. And then the antiderivative of negative cosine is going to be negative sine. So it's going to be negative sine of 5x divided by how much? Now what am I dividing by? Exactly. And then finally, the antiderivative of negative sine is going to be positive cosine of 5x divided by another multiple of 5, so 125. And then So our answer is, and so you can kind of show as much or as little work as you want here. I'm going to show all the work, but really, so yeah, so it's positive x squared times negative cosine of 5x over 5. Minus 2x times negative sine of 5x over 25. Plus 2 times cosine of 5x over 125. Plus c. Now, obviously, you could simplify this as you write it down, right? You're like, oh, a plus times a minus is going to be a minus, or minus times a minus is going to be a plus. So, right, you probably should, as you go, actually write this as, and I might write this as like negative 1/5 x squared times cosine of 5x, and then minus is plus 2/25 x sine of 5x plus 2/25 cosine of 5x plus. That's probably actually how I write my answer down from here to there. But it's okay to take this intermediate step. Would you guys like me to show you how this goes the long way? Which is going to require 2 iterations of integration by parts. It's really okay if the answer is yes, but it's also really okay if the answer is no. All right, the non-responses have it, I guess. It's going to be a no. So what if we were asked to, no, unless someone wants to see it. Yeah, that's how I feel. If someone wants to see it, I'm really happy to do it. But if nobody wants to see it, I get it. I don't want to see it. If we're all cool with it, like yeah, that works, we're good, then you should do it that way. Now, I will point out, you should make sure your teacher is okay with using Tabular if you're doing an integration by parts problem on a test. They should be, but you might want to double check with them just to make sure that it is something that they are okay with. Because sometimes people are like, well, you can't use L'Hopital's rule because we haven't learned it yet. I don't think this really falls into the same category because it's not really a different method. It's just a shorthand notation for the same thing. It's kind of like the thing I never really learned how to do very well. What's that thing called? It's not polynomial division. It's the other fast way of doing polynomial division, which is called, there's a word for it. I don't remember what it is. Synthetic division. Synthetic division is just polynomial division. It's just using shorter notation, but it's still the same work. So I don't think it should be an issue, but you should probably err on the side of double checking with your teacher just to be absolutely 100% sure. Okay, one more problem before we get into some interesting ones. What if someone asked for the integral from 0 to 1 of x to the third e to the x? So let's go x e to the x for a second, actually. Let's just do that. So this is an integration by parts problem. And while you certainly could do it with your limits of integration intact, I really think it's preferable to kind of ignore those for a minute. Meaning, I really would prefer to do the indefinite integral first. And we can use tabular, or we could just do it, since it's a one step, you don't have to use tabular. So you can either use the table and say my u is x, the derivative is 1, the derivative is 0. My dv is e to the x, e to the x, e to the x, right? I really want to strongly emphasize anti-derivatives on this side, even though they're also derivatives, right? But it's anti-derivatives here. Make sure you make them, because it's especially important when it's sine or cosine that you're doing the anti-derivatives, because your plus or minus will vary the opposite way it would for a derivative. So we're going to get x e to the x minus e to the x. That's going to be x e to the x minus e to the x. You can also do it the long way, right? You can say, oh yeah, u is x du is dx, dv is e to the x, v is also e to the x. And so this is going to be equal to u times v minus the integral of v du. Oh yeah, but that's just x e to the x minus e to the x. Either way you want to do it, tabular or not. So then, I like to do all that by itself so that then when I come back here I can say, okay, well this is just going to be x e to the x minus e to the x from 0 to 1. And then it's going to be plug in the 1 times e to the 1 minus e to the 1 minus 0 times e to the 0 minus e to the 0. E minus e, those cancel. And this is going to be minus 0 minus 1. This is going to be 1. The thing I'm trying to help you avoid here is it's really kind of gross to like say, okay, my integral from 0 to 1 of this is equal to, especially if you're not doing the tabular, like, okay, it's x e to the x from 0 to 1 minus the integral from 0 to 1 of e. It's just like, yeah. So I would really strongly encourage everyone, if you are doing an integration by parts problem that's a definite integral, I really think it pays to write it out so that you just do the indefinite integral on its own and then go back and plug back in. Let me show you one more example. Let me try and think of a problem that isn't the tabular problem. Let me think for a second. We can do that. Do I have anything else that's more interesting? We can do that, sure. No, I guess fine. We'll do one of those. Let's say I wanted to do, we can do that. Let's do this. Let's do the integral of x squared times natural log of x. Many people have asked me over the years, can we do tabular here? No, we cannot. Because our u is an x squared, our u is the natural log of x. Also, you don't need tabular because it's a one-step. Oh, but I was going to do this one as a definite integral. Let's do the integral from, no! I'm killing my carpet over here. Let's do the integral from 1 to 3 of x squared natural log of x. I guess I should spray this on the ground while I have this back in here. Okay. Clean that up later. So, again, I'm going to do this on the side. I'm just going to do the indefinite integral of x squared times natural log of x dx. I'm going to let u equal x squared. I'm not going to let u equal x squared. That's it. So this is actually, let's pretend like we didn't catch ourselves right away. U is x squared, du is 2x dx, dv is the natural log of x, and I'm sad to say I've seen people do this too many times. V is 1 over x. You guys know that's wrong. Right? The derivative of the natural log of x is 1 over x. The antiderivative of the natural log of x is the next problem we're going to do, actually. But for now, we don't actually know what the antiderivative of the natural log of x is. We made the wrong choice, right? We were supposed to make u equal to the natural log, right? Lie on it. But I do really, really, really want to remind you guys, the integral of natural log of x is not 1 over x. The derivative of natural log of x is 1 over x. So we're going to let u equal natural log of x. Du is 1 over x dx. My dv, which I should have written down first, is x squared dx. And my v is the antiderivative of that, which is x cubed over 3. So then this is going to end up being uv minus the integral of v du, which is x cubed over 3 times 1 over x dx. Cancel an x. And bring out the 1/3. So rewrite this as natural log of x times x cubed over 3 minus 1/3 integral of x squared. And then the kind of interesting about these natural logs times the power of x is typically when you do dv, you end up doing like the same integral when you get to this part here. So we're going to get natural log of x times x cubed over 3 minus 1/3 times the integral of that, which is x cubed over 3. We don't need a plus c here because we're just doing this for our own kind of use. Right? It's not, the question wasn't do the indefinite integral. The question was do that. We're doing this over here. I'm trying not to step on the stuff I sprayed. Yeah, great. Yeah, good job. You can't even see the green mark anymore. Oh well. So, oh, there it is. I found it. It didn't disappear. Now we're going to write this as the integral, which is natural log of x times x cubed over 3 minus x cubed over 9, right? 3 times 3 is 9, from 1 to 3. And then just plug in. So plug in the 3, I'm going to get natural log of 3 times 3 cubed over 3 is just 3 squared, which is 9, minus 3 cubed over 9, which is just 3. I guess I could show my work, right? Minus, plug in 1, you get natural log of 1 times 1 over 3 minus 1 over 9. 20, so this is 9 natural log of 3 minus 3. Natural log of 1 is just 0, so you get minus minus, you get a plus 1/9. I would probably leave it like that because I was feeling lazy, or I would combine these parts and say I've got minus 27 over 9 plus 1 over 9 is going to be, oh, yeah, that's right, yeah. Maybe it wasn't good to simplify, so minus 27 plus 1 is minus 26 over 9. But really the real point here is that you can integrate, you can do definite integrals of integration by parts problems first by just doing the integration by parts over there, and then after you've done all of the anti-differentiation, you've gotten your antiderivative, then go back and actually write the limits of integration. Don't write these the whole way because it's not fun. Nobody wants to do that. All right. Ooh, let's do that again. Just keep spinning it around and around and around. Reminder, we do have class next Tuesday. We do not have class next Thursday, which is Thanksgiving Day. Nor do we have class on Friday. Not that we have class on Friday, but nobody has class on Friday or Thursday next week. All right. So, I promised you an integral of natural log of x. And so here is kind of the idea. When you are faced with a function that's just like, I have no idea, right? Like, I don't know how to integrate natural log of x. And this is going to be true for natural log of x and also for some inverse trig functions. The idea is to use integration by parts, where, it's right over here, u is the function, because we definitely want to take the derivative of the natural log of x. And just like every other integration by parts problem, dv is everything else that's left, which in this case is, what's left? All right, 1 dx. I'm just going to write dx, but yeah, 1 dx. Derivative, du is 1 over x dx. Antiderivative, which is maybe why you want to write 1. The antiderivative of 1 is just x. Throw it into the formula. So I'm going to get that this is equal to uv, so natural log of x times x, which anyone would write as x natural log of x, minus the integral of v du, x times 1 over x dx. This I'm going to rewrite as x natural log of x minus x times 1 over x is just 1. And the integral of 1 we just did is x. So I get x natural log of x minus x plus c. I do think this integral is worth memorizing, even though your teacher might actually want you to show the work on an exam. Like if someone said, use integration by parts to do this on an exam, they don't want you to just spit out the answer memorized. But this integral comes up just often enough that I do think it's worth your while to memorize that the integral of natural log of x is x natural log of x minus x. Especially if you want to do this next problem. not finding the integral, if I want to make it really hard or just kind of hard. Some people do this problem and it's, yeah, let's not make it super hard. Let's do the integral of natural log of x squared. Yeah. So for this problem, you really only have one choice. And I guess that's not entirely true. I suppose you could try integration by parts, where you let one part, like the u be the natural log, and the other part, the dv, be the other natural log. Usually you're not wanting to let dv equal natural log. Now we know how to integrate natural log, so we could let dv equal natural log. It's still not a good choice. I've never seen a problem, I think, where you actually want to let dv be a natural log. So we're still going to do, we're going to do the same thing we did last time. Well, similar thing we did last time. We're going to let u equal the entire integrand, and dv be the rest. Okay, what's the derivative? Oh, there's some stuff squared. I use a chain rule. There's some stuff squared is going to be 2 times my stuff to the first times the derivative of my stuff. And v is going to be the antiderivative of 1, which is just x. Throw it into the formula. So let's see, we're going to get uv, which I'm going to write the x first. I'm going to write x times the natural log of x squared minus the integral of v du, which is going to be x times 2 times natural log of x times 1 over x dx. And the x's cancel. So I can rewrite this as x times the natural log of x squared minus 2, I bring out the 2, integral of natural log of x. And then if we hadn't memorized the integral of natural log of x, we would do integration of parts again. Since we did, we're just going to say, oh yeah, it's going to be x natural log of x squared minus 2 times the integral of natural log of x, which is x natural log of x minus x. And then we probably want to distribute the minus 2. So we'd write our final answer as x natural log of x quantity squared minus 2x natural log of x plus 2x plus c. Kind of gnarly. And yeah, so I will point out, no one should be asking you any higher powers. Like if someone asks you the natural log of x quantity cubed, you would have to do integration by parts repeated 3 times. And there's no shortcut for it. There's no tabular method for this. You just have to do it. I don't think anyone's asking you that question, but if someone did, that's how you would have to do it. All right, let's look at a couple more examples. A couple more examples of this particular idea. So there are 2 specific functions. I guess really there's 4, but really only 2. There's 2 specific functions that also lend themselves to this particular idea. One of them is, or I should say 2 integrals, is the integral of the inverse tangent of x. And for a fun time, we'll pretend that we're really doing the definite integral from 0 to 1 of inverse tangent of x. But we'll leave that to the end. So we're actually doing this problem, but we know that whenever we do the definite integral, and really whenever we do definite integral in general, it's really just nice to do the indefinite integral, so you don't have to write those limits of integration the whole time. And then, unless it's, if it's integration by parts. So yeah, it's integration by parts. U is inverse tangent. dv is the rest. How exciting. du is, what's the derivative of the inverse tangent? It's a fraction. It's definitely a derivative you need to know, because you know the integral. Meaning, I think we know, and I feel like we talked about how the integral of 1 over 1 plus x squared is the inverse tangent, because the derivative of the inverse tangent is 1 over 1 plus x squared dx. And then our v is just x. So here's what we get. We get something. We get uv, so inverse tangent of x times x. I'm going to write that as x times the inverse tangent of x minus the integral of v du, which is going to be x times 1 over 1 plus x squared, which I'm really going to write as x over 1 plus x squared dx. And now this part is a u sub. Right, so this is my u, that's my dv, but now I'm going to do a u substitution. So I'm going to let u equal 1 plus x squared. And then my du is going to be 2x dx. So that this integral here is going to become, well, 1/2 du is equal to x dx. This integral here is going to become 1/2 du over u. Or if you prefer, 1/2 integral of 1 over u du. And what's the integral of 1 over u? It's the natural log of the absolute value of u. And then plugging back in u, it's 1/2 the natural log of the absolute value of 1 plus x squared. So that's what this integral is here. It's 1/2 the natural log of the absolute value of 1 plus x squared. So my answer here is x times the inverse tangent of x minus 1/2 the natural log of the absolute value of 1 plus x squared plus c. One thing you might notice if you see other people do this is a lot of people don't write the absolute values here, not because they're not necessary, well, I guess they are necessary, not because they aren't part of the integral there, but because 1 plus x squared is always positive. So you can just drop the absolute values because the absolute value of something positive is just something you've got inside. So you'll often see that whenever you have a natural log of a thing where the inside part's always positive anyways, you'll often see people just drop the absolute values. All right, so now to answer the actual question, what do we get when we do the definite integral, this from 0 to 1? Well, we're going to get this thing evaluated from 0 to 1, which I feel like I don't have enough room for, so let's go to the other side. Definitely not an integral you should memorize. I definitely have never memorized that one. It's definitely one you're going to want to work out every time you get asked it. So if I'm trying to do the integral from 0 to 1 of the inverse tangent of x dx, that's going to equal the thing I just found, which was, I think it was x inverse, that is far worse. X inverse tangent of x minus 1/2 the natural log of the absolute value of 1 plus x squared from 0 to 1. And I'm not writing the plus c because it's a definite integral. So that's going to be 1 times the inverse tangent of 1 minus 1/2 the natural log of 1 plus 1 is 2. Notice I didn't write the absolute values because 2 is already positive. Minus, plug in 0, 0 times the inverse tangent of 0 minus 1/2 natural log of 1. Okay, what's the inverse tangent of 1? Let me ask you differently. What's the angle that if I take tangent of that angle, it's equal to 1? Yeah, exactly pi over 4. This is 1/2 natural log of 2. And the rest of that's 0. 0 times doesn't matter, but inverse tangent of 0 is also 0, and natural log of 1 is also 0. So that's your final answer. Neat. And I suppose we should do the other one. So I will point out, you could do a very similar process for inverse cotangent. because the derivative of inverse cotangent is negative 1 over 1 plus x squared. Nobody ever talks about inverse cotangents anymore. The other one that I want us to look at, because it does come up, is the integral of the inverse sine. And this is going to work out in a very, very similar way. We're going to let u equal inverse sine of x. We're going to let dv be the rest. Our derivative here, so the derivative inverse sine is 1 over the square root of 1 minus x squared dx. And v here is just x. These inverse trig derivatives are important to know, right? We learned them in Calc 21A, but I know it's been a while, so make sure you remember your inverse trig derivatives. They are kind of especially helpful, especially once you start talking about trig substitutions. So this is going to end up being u times v, so x times the inverse sine of x minus the integral of v du, which is going to be x over the square root of 1 minus x squared dx. And just like before, we can do a u substitution. We can let u equal 1 minus x squared. Du is going to be negative 2x dx. So negative 1/2 du is x dx. So I can rewrite this as, I'm just going to write it this way. It's x inverse sine of x minus negative 1/2 integral of x dx becomes the du, or x dx becomes the negative 1/2 du. And this is 1 over the square root of u, which I'd really rather write as u to the negative 1/2. Integrate. We get x inverse sine of x. I know this is weird to have x's and u's. I'm probably kind of abusing notation here. It's no big deal. Plus, I mean, it's a tiny big deal, but it's not really a big deal. Plus 1/2. Integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, or times 2. Oh, those cancel. And then finally, u is 1 minus x squared. So this is x inverse sine of x plus 1 minus x squared to the 1/2, or preferably the square root of 1 minus x squared. You can definitely find these integrals in any table, like at the beginning of the back of your book, there's a table with like 200 integrals in it. This one and inverse tangent and logarithm are all definitely on that table, but it is a process we should be able to do. Let's see. Oh, that seems worthwhile. Sometimes things are extra tricky. Like, what if I was asked to integrate sine of the square root of x? Well, shoot, I don't know. So when I'm at a loss, I usually start thinking u substitution. At least I usually am always thinking, really, like, I'm like, can I do a u sub? Can I do a u sub? Right? Is a u sub possible? That's usually my first thought process, because a u sub is usually, a u sub, okay, yeah. A u sub is usually easy. Although it's not going to be that easy this time, but it's sort of easy. So let's let u equal kind of the only thing that makes sense, which is the square root of x. Now, it's not going to be super helpful to find du. I'll find it just to show you guys, but du is going to be 1 over 2 root x dx. Some people like to do this. Some people totally do this, and then they solve for dx, and say dx equals 2 root x du, and then like, oh, but look at that, dx is really 2u du. This is not the way I do it, but it is the way that's fine. There's actually what I think is an easier way. So instead of trying to find du in terms of dx and then solve for dx and then replace this, the easier thing to do first is just solve for x, square both sides. Take the derivative of both sides. What's the derivative of u squared? 2u du. What's the derivative of x? It's dx. Oh, that looks a lot like that. Either way is fine. So look what we get now. We get the integral of sine of u times 2u du. And now we're in an integration by parts situation. Because you've got a trig thing times an algebra thing. And we dumbly already used up our u. So I don't want to use u again because that's going to be confusing. So instead of using u, I typically use w if I don't confuse u. So I'm going to do, instead of doing u and dv, I'm going to use w and dv. So w should be what? Sine of u or 2u? Well, I suppose a normal person will probably factor out the 2. So, should my u be the trig thing or the algebra thing? Right, exactly. So w is u, and then dv is the rest, sine of u du. dw is du. It's also dark-winged duck. And v is the antiderivative sign, which is negative cosine. In case you don't know dark-winged duck, you're missing out. When there's trouble, you call dw dark-winged duck. Yeah, okay. Anyway, sorry, getting a little carried away. Where was I going? Oh yeah, so now we're just going to throw this in the formula. So again, instead of the formula being uv minus the integral of v du, it's going to be wv minus the integral of v dw. Because we're using w instead of u. The thing about integration by parts is that when you do integration by parts, even though you're using these other variable names, you're still just ending up with the same variables you started with. So I'm starting with an integral in terms of u, and I'm still going to get an integral in terms of u. Right? I'm going to get wv, which is really u times negative cosine of u, minus the integral of v dw. So minus a minus cosine of u du. Right? I still have all the same variables. And then we integrate this. We get negative u cosine of u. Integral of cosine is positive sine. And then we go back to our original, and we plug in that u is square root of x. So this is actually equal to negative square root of x cosine of square root of x plus the sine of root x plus c. Sorry, I got a little messy there. So sometimes a problem might not look like it's going to have an integration by parts, but there's an integration by parts hidden in it. Let us look. Okay, let me ask you guys. Do you want to see the integral of secant cubed? Is that something anyone has talked about? We can save it for next time if you guys don't want to talk about it today. Next time. All right, sounds good. So let's do this last problem here. Let's do the integral of x cubed e to the x squared. And here's a good thing to be aware of. E to the x squared is not antidifferentiable, at least not in any sort of regular way. There are definitely computer programs that can integrate a definite integral e to the x squared, and it's actually a super important integral, right? If you've ever taken a stats class, you've definitely looked at the integral of e to the negative x squared dx. That's your z table, where the area under this curve is just the area, is just the z value for whatever you're looking at. Anyway, but the point is you can't integrate this, right? There's no nice elementary function whose derivative is equal to e to the negative x squared, or e to the positive x squared. Really, e to the anything super complicated. So I can't really do integration by parts here, because I can't let dv be this, because I don't know how to integrate that. We can't, and not just that I don't know, we cannot integrate that. So I mean, I could try integration by parts with u equal to, letting u equal this seems like a poor choice, because u being that, the derivative is going to be e to the x squared times 2x. Seems like you're going to make things just more complicated, so that seems like the wrong way to go. So again, when I'm in doubt, I kind of go to u substitution. I'm going to let u equal the only thing that I think makes sense, which is x squared. Why not x cubed? Well, because x cubed isn't trapped inside another function. Also because although the derivative of x cubed is 3x squared, I don't have an x squared times dx. I have an x squared in my exponent. So typically, if I have to choose between the two things of how I choose my u for u substitution, I'm always defaulting to picking u to be something that's stuck inside another function. Du is going to be 2x dx. And while I don't have an x dx, well, actually, I kind of do have an x dx. I could totally write this as the integral of x squared times e to the x squared times x dx, right? Breaking that x cubed up into an x squared times an x. And then the x dx is going to be 1/2 du. And well, look, I'm good to go now, because my e to the x squared is e to the u, and my u squared is, sorry, my x squared is u. So now I'm really integrating 1/2 the integral of u e to the u. And instead of doing integration by parts, one step, let's take a table. Let's do a tabular. My w is going to be u, and the derivative of u is 1, and the derivative of 1 is 0. And my dv is going to be e to the u, and the antiderivative of e to the u is e to the u, and the antiderivative of e to the u is e to the u. So it's plus u e to the u minus 1 times e to the u. So this is going to end up equaling 1/2 u e to the u minus e to the u. And then we plug back in that u is x squared. So this is really 1/2 x squared e to the, e to the x squared minus e to the x squared. Kind of neat.